Look up at the night sky. What do you see? Pinpricks of light, distant worlds, the soft glow of galaxies stretching beyond sight. But what if I told you every single one of those celestial wonders shares a secret? They're all part of the same grand story, a cosmic epic that began with a single, unimaginable moment, the Big Bang. Think about that for a second. The air you're breathing, the ground beneath your feet, even the screen you're staring at right now, every atom, every particle, traces its existence back to that explosive birth of the universe. It's a story written across 14 billion years, and today we're going to unravel it together. This isn't just a tale of distant stars and cold, empty space. It's your story too. The iron in your blood was forged in the hearts of dying stars. The carbon in your cells was scattered across the cosmos by ancient supernovae. You are quite literally made of stardust, and that's just the beginning. From the searing heat of the Big Bang to the icy silence of the universe's farthest reaches, we'll explore how everything came to be, how clouds of gas became galaxies, how tiny fluctuations grew into the vast structures we see today, and why the universe looks the way it does. But here's the thing, this story isn't finished. Even now, scientists are peering into the depths of space, uncovering mysteries that challenge everything we thought we knew. Dark energy stretching the universe apart, black holes warping the fabric of reality, planets that might harbor life. So why does this matter? Because understanding where we came from changes how we see ourselves. It's humbling, sure, to realize how small we are in the grand scheme of things. But it's also exhilarating to know we're part of something so vast, so ancient, and so beautifully interconnected. By the time we're done, you won't just see the night sky differently, you'll feel it. The cosmos isn't just out there, it's in you, around you, woven into the very fabric of existence. So let's begin this journey from the first spark of creation to the edge of everything we know and beyond. The universe has been waiting 14 billion years to tell its story. Are you ready to listen? 13.8 billion years ago, in a flash of energy so intense it defies comprehension, our universe was born. Picture this, not an explosion in space, but the birth of space itself, time unfurling like a cosmic ribbon, and matter blinking into existence where there was only nothingness before. This was the Big Bang, the ultimate Genesis story. In less time than it takes to blink, the infant universe expanded from smaller than an atom to the size of a galaxy, a runaway growth spurt scientists call inflation. Energy didn't just exist here, it was the universe, a seething ocean of potential. Then something miraculous happened. That energy began to crystallize into the first particles, like droplets condensing from steam. Quarks, the tiniest building blocks of matter, danced into being, soon clumping together to form protons and neutrons, the same particles that would one day make up stars, planets, and even you. But how do we know any of this actually happened? The evidence is written in the oldest light in existence, the cosmic microwave background. It's a faint glow, a whisper of heat left over from the Big Bang itself, stretching across the entire sky like a fossilized fingerprint of creation. When scientists tune their telescopes to this ancient radiation, they're essentially peering back to a time when the universe was just a newborn, hot and dense as a freshly forged star. What's even more astonishing is that tiny fluctuations in this background glow, imperceptible ripples, became the seeds for everything we see today. Those slight variations in density, smaller than a grain of sand in a desert, grew under gravity's pull to become galaxies, clusters, and the vast cosmic web that structures our universe. Here's the wildest part: the Big Bang wasn't just an event, it's still happening. the universe keeps expanding, carrying galaxies away from each other like dots on an inflating balloon. And yet, despite all we've discovered, mysteries remain. What triggered that initial explosion? What existed, if anything, before time began? These questions push the limits of human understanding, reminding us that the universe's origin story is far from complete. But one thing's certain: every atom in your body, every star in the sky, every planet orbiting a distant sun exists because of that singular, unimaginable moment when everything began. The Big Bang didn't just create the cosmos, it set the stage for you. Imagine a universe so hot and dense that even atoms couldn't survive. This was reality mere microseconds after the Big Bang. The newborn cosmos wasn't filled with stars or planets, but with a churning, superheated soup of the most basic building blocks of matter, quarks and gluons. These weren't just particles, they were free-flowing ingredients in a cosmic furnace, bouncing around at temperatures exceeding trillions of degrees. Under such extreme conditions, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were still unified into a single, all-powerful interaction. Here's what makes this era so fascinating. Quarks, which normally cling together in groups to form protons and neutrons, couldn't form stable bonds in this unimaginable heat. Instead, they zipped around freely like marbles in a high-speed blender, constantly colliding and exchanging gluons, the glue particles that hold atomic nuclei together. Scientists call this chaotic state quark-gluon plasma, and it's the closest thing to the original state of the universe we can imagine. But how do we study something that existed for just a fraction of a second billions of years ago? The answer lies in some of humanity's most incredible machines, particle colliders like the Large Hadron Collider. By smashing heavy ions together at nearly the speed of light, physicists can briefly recreate those primordial conditions, producing tiny droplets of quark-gluon plasma that last for mere fractions of a second. These experiments reveal astonishing truths. For instance, this plasma behaves more like a perfect liquid than a gas, flowing with virtually no friction. As the universe expanded and cooled, something remarkable happened around 1 microsecond after the Big Bang. The temperature dropped enough for quarks to finally stick together, forming the first protons and neutrons, the cores of future atoms. This transition, known as hadronization, was like watching random puzzle pieces suddenly snap into recognizable shapes. The strong nuclear force, one of the four fundamental forces, finally had the upper hand, binding quarks into stable arrangements that would persist for billions of years. What's truly mind-bending is that every proton in your body right now, every one in every atom, is a direct descendant of those first particles formed in that unimaginable heat. They've survived supernova, cosmic collisions, and 14 billion years of cosmic history just to become part of you. And the gluons, they're still at work today, holding atomic nuclei together with unimaginable strength. Without them, matter as we know it would simply fly apart. This quark-gluon plasma phase wasn't just a curious footnote in cosmic history, it set the stage for everything that followed. The precise way quarks combined determined how much normal matter would exist in the universe, how quickly stars could form, and ultimately how life could emerge. Even now, remnants of this era might exist in the cores of neutron stars, where matter is compressed so tightly that it might briefly return to this primordial state. So the next time you look at your hand, remember, you're holding a piece of the universe that once existed as pure, unbridled energy, a testament to the incredible transformations our cosmos has undergone since those first fiery moments. For nearly 400,000 years after the Big Bang, the universe remained a swirling fog of charged particles, protons and electrons dancing in a scorching plasma too energetic to combine. Then, in what scientists call recombination, the cosmos finally cooled to around 3,000 degrees, cool enough for electrons to be captured by atomic nuclei, forming the very first stable atoms. Picture this cosmic milestone like steam condensing into water droplets after a long, hot shower. The moment those first hydrogen atoms formed, something extraordinary happened. Light, which had been trapped bouncing between particles like a pinball, could suddenly travel freely across the universe. This released glow is what we now detect as the cosmic microwave background, the oldest snapshot of our universe, frozen in time. But why did hydrogen and helium dominate this new atomic landscape? The answer lies in the extreme conditions of the early universe. In those first few minutes after the Big Bang, when temperatures were still hot enough for nuclear fusion, protons and neutrons combined to form light atomic nuclei, a process called Big Bang nucleosynthesis. Hydrogen, with its single proton, was the simplest and most abundant result. Helium came next as pairs of protons and neutrons locked together. Heavier elements couldn't form yet because the universe expanded and cooled too quickly, cutting this initial fusion phase short. The result, a cosmos made of roughly 75% hydrogen and 25% helium by mass, a recipe that would shape everything to come. These two elements became the cosmic building blocks for the first stars. Without them, the universe would have remained an endless, lightless sea of scattered particles. But here's what's even more mind-blowing. When we look at the night sky today, we're still seeing the legacy of that primordial chemistry. The sun, for instance, is mostly hydrogen fusing into helium, the same process that ignited the very first stars. The helium in birthday balloons, it's directly descended from those first atoms forged in the infant universe. Yet recombination wasn't just about creating atoms, it fundamentally changed how the cosmos evolved. Before this event, matter was so densely packed that gravity struggled to pull structures together against the pressure of radiation. But once neutral atoms formed, the universe became transparent, allowing matter to clump more easily under gravity's pull. Those tiny density fluctuations we see in the cosmic microwave background, they became the seeds for galaxies. In fact, without this shift, the cosmic web of galaxies we know today might never have formed. What's equally fascinating is how delicate this balance was. If the universe had cooled just slightly faster or slower, the ratio of hydrogen to helium might have shifted dramatically, potentially altering the lifespan of stars, the formation of planets, and even the chemistry of life itself. The fact that we exist to ponder these questions is a testament to how precisely those first atoms came together. Every breath you take fills your lungs with nitrogen and oxygen elements that wouldn't exist if those primordial hydrogen clouds hadn't first collapsed into stars. So when astronomers point their telescopes at distant gas clouds, they're not just looking at raw material for new stars. They're glimpsing the unchanged remnants of that ancient era, preserved like cosmic fossils. And here's the kicker, some of that hydrogen drifting between galaxies today has never been inside a star. It's the same pristine matter that formed when the universe was just a toddler, unchanged for over 13 billion years. That means parts of your body, woven from stardust, share a lineage with gas that has outlived entire generations of stars, a connection stretching back to the very first atoms. This era didn't just give the universe its first tangible matter, it set in motion the chain of events that would eventually lead to galaxies, planets, and life. The simplicity of hydrogen and helium belies their cosmic importance. They were the quiet pioneers, the humble beginnings of everything complex that followed. Without them, the night sky would be empty, the stars would never have ignited, and the story of the universe would have ended before it truly began. After the glow of recombination faded, the universe plunged into an abyss unlike anything we can imagine, a time so devoid of light that astronomers call it the cosmic dark ages. Picture an endless sea of hydrogen and helium gas, stretching across the entire cosmos without a single star to break the monotony. No galaxies spun in the void, no quasars blazed with energy, just an infinite, uniform darkness where time seemed to stand still. This wasn't merely the absence of stars, it was a universe still gathering its breath, waiting for gravity to work its magic. What made this era so peculiar was the sheer simplicity of it all. The universe had cooled enough for atoms to exist, but not yet enough for structures to form. Without heavy elements or dust to absorb and re-emit light, space was eerily transparent, almost ghostly. If you could travel back to this time, your eyes would perceive nothing but blackness in every direction, even though the cosmos was filled with matter. The only thing breaking the silence would be the faint whisper of hydrogen atoms absorbing and emitting radio waves at a specific frequency, a signal modern astronomers call the 21-centimeter line, our best window into this shadowy epoch. Yet within this apparent stillness, subtle dramas were unfolding. Tiny fluctuations in density left over from the Big Bang, those same ripples we see in the cosmic microwave background, were slowly amplifying under gravity's relentless pull. Regions where gas was slightly denser than average began drawing in more material, growing ever so slightly heavier over millions of years. It was an agonizingly slow process, like watching a mountain form one grain of sand at a time, but it set the stage for a revolution. The end of the Dark Ages didn't come suddenly. Instead, pockets of gas reached critical densities, collapsing under their own weight until the pressure and temperature at their cores sparked nuclear fusion. The first stars, known as Population 3 stars, burst into existence not in isolation, but in clusters scattered across the cosmos. These weren't like the stars we know today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously hot and dying young in spectacular supernovae. Their light didn't just illuminate the universe, it transformed it, breaking apart neutral hydrogen atoms into ions and initiating the epoch of reionization. Here's what's truly astonishing. We may have already glimpsed remnants of this era. The James Webb Space Telescope peering deeper into space and further back in time than any instrument before it has detected galaxies that appear impossibly mature for their age. Some scientists speculate these could be among the very first structures to emerge from the Dark Ages, challenging our understanding of how quickly the universe woke up. The Dark Ages weren't just a gap in cosmic history, they were a necessary pause, a quiet before the storm that shaped everything to come. Without this extended period of darkness, matter wouldn't have had time to clump together in just the right way to form galaxies. The first stars wouldn't have seeded the universe with heavier elements, paving the way for rocky planets and eventually life. Even the vast cosmic web, with its filaments and voids, owes its structure to the delicate gravitational dances that began during this seemingly featureless era. So when astronomers study this period, they're not just filling in a blank spot on the cosmic timeline, they're uncovering the origin story of complexity itself. The Dark Ages remind us that even in the emptiest, most uneventful stretches of time, the universe was quietly preparing for the dazzling display of stars, galaxies, and planets we see today. And in a way, that's the most humbling lesson of all. Darkness isn't the absence of creation, it's the canvas upon which light is painted. The cosmic Dark Ages shattered when the first stars ignited, not with a gentle flicker, but with a blaze so intense it rewrote the rules of the universe. These weren't just any stars, known as population 3 stars. They were titans hundreds of times more massive than our Sun, burning at temperatures that would make modern stars seem like candles in comparison. Picture a celestial furnace so powerful it could vaporize entire solar systems in seconds, its light piercing the primordial darkness for the first time in hundreds of millions of years. What made these stars truly unique wasn't just their size, it was their purity. Born from pristine clouds of hydrogen and helium left over from the Big Bang, they contained not a speck of heavier elements. No carbon, no oxygen, no iron. This purity forced them to burn hotter and faster, like pouring gasoline on a campfire. Their nuclear reactions didn't just fuse hydrogen into helium, they forged entirely new elements in their cores, cooking up the first traces of carbon, nitrogen, and oxygen through a runaway chain of reactions. But these stars weren't destined to shine for long. Their incredible mass meant they lived fast and died young, collapsing in cataclysmic supernova after just a few million years, a blink in cosmic terms. These explosions did more than just light up the early universe. They scattered their newly forged elements across space like cosmic gardeners sowing seeds. For the first time, the universe wasn't just hydrogen and helium. It had the raw ingredients for planets, oceans, and even life. Here's the twist: we've never directly observed a population 3 star. They burned out so quickly that even our most powerful telescopes can't peer far enough back to catch them shining. Instead, scientists hunt for their fingerprints in the chemical composition of later stars. Ancient stars in our galaxy's halo, like the faint red dwarf E1 523-0901, contain barely any heavy elements, clues that they formed from the ashes of those first supernovae. It's like finding a piece of pottery made from clay mined in a long-lost civilization. The legacy of these stellar pioneers is everywhere around us, the oxygen you're breathing right now. Every atom was forged in a star, likely one of those first-generation giants. The calcium in your bones, the iron in your blood, all of it was scattered across the cosmos by explosions that occurred billions of years before Earth existed. Even the gold in your jewelry was probably created when 2 neutron stars collided, a process only possible because population 3 stars first seeded the universe with heavier elements. What's even more mind-bending is how these stars shaped the universe's future. Their intense ultraviolet radiation ripped electrons from hydrogen atoms, reionizing the cosmos and ending the Dark Ages for good. This process wasn't gentle, it was a violent upheaval that took hundreds of millions of years, like a forest fire clearing the way for new growth. Without it, later stars might have formed in denser, more isolated pockets, drastically altering the distribution of galaxies we see today. Some theories suggest these first stars didn't die alone. They might have collapsed directly into black holes, seeding the early universe with the gravitational anchors around which galaxies would eventually form. Others speculate that a few population 3 stars could still exist in the most remote corners of space, their light too faint for us to detect. Whether they're gone or just hiding, their influence is undeniable. They turned a universe of simple gases into a chemical playground, setting the stage for every planet, every living thing, and every wonder we've yet to discover. So when you gaze at the night sky, remember, you're not just looking at stars, you're seeing the descendants of those first cosmic pioneers, the ones who transformed a dark, empty universe into a place where complexity and eventually consciousness could take root. Their light may be gone, but their story is written in every atom of your being. Gravity's patient work didn't stop with the first stars, it was just getting started. As those massive population 3 stars died in spectacular supernova, their remnants didn't simply vanish. Instead, they became the raw materials for something far grander, the first galaxies. Imagine these protogalaxies not as the majestic spirals we know today, but as cosmic toddlers, clumsy, chaotic, and full of potential. Swarms of stars, gas clouds, and the invisible grip of dark matter swirled together in a gravitational dance that would shape the universe's future. Dark matter, that mysterious substance that neither emits nor absorbs light, was the unsung architect of this transformation. While ordinary matter, the stuff of stars and planets, could clump together, it was dark matter's vast, invisible halos that provided the gravitational scaffolding for galaxies to form. Think of it like an invisible framework holding up a skyscraper. Without it, the entire structure would collapse. Computer simulations of the early universe show this vividly. Wherever dark matter pooled most densely, ordinary matter followed, like iron filings drawn to a magnet. The first galaxies were nothing like Andromeda or the Milky Way. They were tiny by modern standards, perhaps only 1% the mass of our galaxy, and brimming with young, hot stars that lit them up like cosmic fireflies. Turbulent and violent, these protogalaxies frequently collided and merged, growing larger with each encounter. Some devoured smaller neighbors whole, while others stretched into elongated streams of stars under gravity's relentless pull. Over billions of years, these mergers would sculpt the majestic spirals and ellipticals we recognize today. Here's what's astonishing: we can still see echoes of this era in our own galactic backyard. The Milky Way's halo contains ancient star clusters and rogue stars moving in odd orbits, relics of smaller galaxies it absorbed long ago. It's like finding prehistoric tools buried in your garden, evidence of a time when your neighborhood looked utterly different. Even more remarkable, some of these early galaxies still exist in pristine form. Ultra-faint dwarf galaxies like Segway 1, barely visible against the night sky, are essentially living fossils unchanged for billions of years, their stunted growth a snapshot of the universe's youth. But why did some galaxies become spirals while others grew into smooth, football-shaped ellipticals? The answer lies in their violent histories. Spiral galaxies like ours avoided major collisions, allowing their delicate disks to spin undisturbed. Ellipticals, on the other hand, are the products of catastrophic mergers, cosmic car crashes that scrambled their stars into random orbits. The largest galaxies, like the supergiant IC1101, sit at the centers of galaxy clusters, having devoured countless smaller neighbors over eons. None of this could have happened without dark matter's guiding hand. Its gravitational influence didn't just shape individual galaxies, it orchestrated the universe's large-scale structure. Vast filaments of dark matter formed a cosmic web, with galaxies strung along them like pearls on a necklace, the empty voids between these filaments. They're not truly empty, just regions where dark matter's pull was too weak to gather much ordinary matter. This intricate architecture, built over billions of years, determines where galaxies live, how they move, and even their ultimate fate. So when astronomers map the distribution of galaxies today, they're not just making a celestial census, they're decoding gravity's grand design, a blueprint written in the aftermath of the first star's death. Every galaxy, from the tiniest dwarf to the largest cluster, carries the indelible imprint of those early chaotic mergers. And somewhere in that cosmic construction project, one unremarkable protogalaxy began a journey that would lead against unimaginable odds to you. Black holes weren't just cosmic accidents, they became the gravitational anchors around which galaxies took shape. Imagine a force so powerful it warps space and time, swallowing stars whole and bending light into impossible curves. Yet these terrifying objects, especially the supermassive ones at galactic centers, played a paradoxical role. They didn't just destroy, they helped build the universe as we know it. Take Sagittarius, a star, the black hole at the heart of our Milky Way. Though 4 million times the Sun's mass, it's remarkably quiet compared to its distant cousins supermassive black holes called quasars, which outshine entire galaxies with their energy. How did these monsters grow so large so quickly? That's one of astronomy's biggest puzzles. Some theories suggest they formed directly from collapsing clouds of primordial gas, skipping the star stage entirely. Others propose they grew from smaller black holes, stellar remnants left by the first stars, merging over and over like cosmic snowballs rolling downhill. The truth might be even stranger. Recent discoveries of billion solar mass black holes in galaxies just 700 million years after the Big Bang suggest they had a head start, possibly seeded by exotic physics we don't yet understand. Their influence on galaxies is undeniable. As these black holes devour gas and dust, they don't just consume, they transform. Matter spiraling into the abyss heats up to millions of degrees, creating jets of energy that can stretch across thousands of light years. These jets act like cosmic blowtorches, heating surrounding gas so violently they prevent new stars from forming. It's a self-regulating system. The more a black hole feasts, the more it stifles its own galaxy's growth. This delicate balance explains why we don't see galaxies much larger than those we observe today. But here's the twist: black holes might also be galactic gardeners. By limiting star formation, they ensured galaxies didn't burn through their fuel too quickly, allowing stable, long-lived systems like our Milky Way to emerge. Their gravitational pull organizes stars into orderly orbits, creating the majestic spirals we recognize. Even more remarkably, the heavy elements forged in their accretion disks, gold, platinum, uranium, were scattered across the cosmos when quasars erupted, enriching future generations of stars and planets. The James Webb Space Telescope has spotted something astonishing: tiny, ancient galaxies with disproportionately massive black holes, suggesting these gravitational giants might have formed before their host galaxies did. This flips our understanding on its head. Instead of black holes growing inside galaxies, maybe galaxies grew around black holes. If true, it would mean these cosmic engines didn't just influence galaxy evolution, they kickstarted it. Yet for all their power, black holes remain deeply mysterious. We still don't know what happens inside one, where the laws of physics as we know them break down completely. Some theories suggest they might be portals to other universes or cosmic factories for exotic particles. Others propose they slowly evaporate over eons, leaking energy back into space. What's certain is that without them, the universe would look radically different. No glittering spirals, no blazing quasars, just scattered stars adrift in darkness. They are the universe's silent architects, shaping its structure from the shadows while hiding their deepest secrets behind an event horizon no light can escape. So when astronomers peer into the heart of distant galaxies, they're not just studying black holes, they're uncovering the invisible hands that molded the cosmos. These gravitational titans remind us that destruction and creation are two sides of the same cosmic coin, and that even the most fearsome forces in nature can give rise to the conditions that make life possible. The Milky Way isn't just a smear of stars across the night sky. It's a dynamic, evolving structure with a dramatic backstory. Picture a cosmic construction project spanning nearly 13 billion years, where gravity assembled stars, gas, and dark matter into the magnificent spiral we call home. Our galaxy didn't form in isolation. It grew by swallowing smaller neighbors, each collision leaving behind traces like celestial breadcrumbs. The Gaia Space Telescope has mapped streams of stars, ghostly remnants of ancient galaxies torn apart by the Milky Way's gravitational pull. One of these, the Gaia Enceladus galaxy, merged with ours around 10 billion years ago, its stars now woven into our galaxy's halo like threads in a tapestry. What makes the Milky Way special isn't just its size, it's its architecture. Unlike simple spirals, we live in a barred spiral galaxy with a central bar-shaped structure of stars connecting the arms. This bar acts like a cosmic mixer, funneling gas toward the center and fueling star birth. Our Sun orbits about 27,000 light-years from this bustling core, completing a lap every 230 million years, a journey it's made roughly 20 times since the dinosaurs roamed Earth. Surrounding the disk is a vast halo of dark matter, invisible but crucial, weighing as much as 1 trillion suns and holding everything together with its gravitational grip. At the galaxy's heart lies Sagittarius, a star, a supermassive black hole 4 million times heavier than our Sun. While it's relatively quiet now, evidence suggests it was once a blazing quasar, devouring matter and lighting up the early universe. Today, it's more like a sleeping giant, occasionally flaring when stray gas clouds venture too close. Yet its influence is everywhere. Stars near the galactic center whip around it at thousands of kilometers per second, their orbits revealing the black hole's immense mass. Without this gravitational anchor, the Milky Way might never have formed its distinctive spiral pattern. But how do we study a galaxy we're inside of? It's like trying to map a forest while standing among the trees. Astronomers use ingenious tricks, like tracking the motions of pulsars, dead stars that emit precise radio pulses to measure distances. Infrared telescopes peer through dust clouds to reveal the galaxy's structure, while radio telescopes trace vast hydrogen rivers flowing between the spiral arms. These observations paint a picture of a galaxy still growing, still changing. Right now, the Milky Way is digesting the Sagittarius dwarf galaxy, whose stars are being strewn across our sky in a slow-motion disintegration. The Milky Way's story is far from over. In about 4 billion years, it will collide with the Andromeda galaxy in a cosmic dance that will reshape both. Stars will be thrown into new orbits, gas clouds will ignite in bursts of star formation, and the two supermassive black holes will eventually merge, sending gravitational waves rippling through space-time. Yet amid this chaos, our solar system will likely survive unscathed, a speck in a grand reconstruction project. Understanding our galaxy isn't just about mapping stars, it's about context. The Milky Way is one of 2 trillion galaxies in the observable universe, each with its own story. By studying our cosmic neighborhood, we're piecing together how galaxies evolve, how they birth stars and planets, and ultimately how rare or common worlds like ours might be. Every time you look up at the Milky Way, you're not just seeing stars, you're gazing at the cumulative history of mergers, explosions, and rebirths that made your existence possible. Long before the Sun became the blazing star we know today, it was just a whisper in a vast molecular cloud, a cold, dark region of space where gas and dust drifted like cosmic flotsam. Then, about 4.6 billion years ago, something extraordinary happened. Perhaps triggered by the shockwave from a nearby supernova, or simply the slow accumulation of gravity's pull, this cloud began to collapse. As it contracted, it spun faster, flattening into a disk with a dense, hot core at its center. Within this stellar nursery, the raw ingredients for our solar system swirled in chaotic harmony. At the heart of this maelstrom, the infant sun grew hotter and denser, its core reaching temperatures of millions of degrees until nuclear fusion ignited a process where hydrogen atoms smashed together to form helium, releasing unimaginable energy. This moment marked the birth of our sun, a fiery beacon in the darkness, but the real magic happened in the disk surrounding it. Tiny dust grains, no larger than specks of smoke, began sticking together through electrostatic forces, forming pebbles, then boulders, and eventually planetesimals, the building blocks of planets. The inner solar system was a violent construction zone. countless planetesimals collided, some shattering, others merging into larger bodies. This chaotic dance gave rise to the rocky planets Mercury, Venus, Earth, and Mars. Farther out, where temperatures plummeted, volatile ices like water, methane, and ammonia clung to dust grains, creating the gas giants Jupiter and Saturn, along with the ice giants Uranus and Neptune. Jupiter's immense gravity played a pivotal role, acting as a cosmic vacuum cleaner, hurling dangerous asteroids away from the inner planets or swallowing them whole. Without this protective influence, Earth might have been bombarded into oblivion before life could take hold. Earth's position in the habitable zone, that Goldilocks region where liquid water can exist, wasn't just luck. It was the result of countless variables aligning perfectly. A fraction closer to the Sun and our oceans would have boiled away. A fraction farther and the planet might have frozen solid. But Earth's fortune didn't end there. A colossal impact with a Mars-sized body named Theia not only gave us our moon but also tilted Earth's axis, creating the seasons that would later drive the diversity of life. The moon's steady gravitational pull stabilized Earth's rotation, preventing wild climate swings that could have made complex life impossible. Even the leftovers of this planetary construction project played crucial roles. The asteroid belt, a graveyard of failed planet formation, became a reservoir of raw materials. Comets, icy remnants from the outer solar system, delivered water and organic molecules to early Earth, seeding the chemistry for life. Every planet, every moon, every speck of dust in our solar system carries the fingerprints of this ancient process, a story written in rock, ice, and gas. What's truly humbling is how fragile this balance was. Change one variable, the Sun's mass, Jupiter's orbit, the angle of Earth's tilt, and our solar system might have looked radically different. No gas giants, no rocky planets, or worse, no stable home for life at all. Yet here we are, on a pale blue dot suspended in a beam of sunlight, the product of 4.6 billion years of cosmic craftsmanship. The next time you feel the warmth of the sun on your skin, remember, you're standing in the glow of a stellar nursery's most extraordinary gift. Earth's earliest days were anything but peaceful, a roiling, molten nightmare where the surface resembled more of a bubbling cauldron than a planet. For millions of years after its formation, Earth remained a scorching wasteland, bombarded relentlessly by asteroids and comets left over from the solar system's chaotic construction. The heat from these collisions, combined with radioactive decay deep within the planet, kept the surface a seething ocean of magma. There were no continents, no oceans, just a glowing, liquid landscape beneath a thick, toxic atmosphere of carbon dioxide, nitrogen, and water vapor. But then, something remarkable happened. As the barrage of impact slowed, Earth finally began to cool. The first solid crust formed, thin and fragile, like a skin forming over cooling soup. Water vapor trapped in the atmosphere condensed into torrential rains that lasted for millennia, filling the lowest basins and creating the very first oceans. These weren't the calm, blue waters we know today. They were acidic, scalding, and rich in dissolved minerals, a chemical soup that would become the cradle of life. Meanwhile, volcanic outgassing continued to shape the atmosphere, releasing nitrogen, carbon dioxide, and traces of methane, a far cry from the breathable air we enjoy now, but the first steps toward a stable environment. The real turning point came when life emerged, not as complex organisms, but as simple, single-celled microbes. The exact moment life first stirred remains one of science's greatest mysteries, but fossil evidence suggests it happened astonishingly fast, perhaps as early as 4.1 billion years ago. These pioneer organisms, likely extremophiles thriving near hydrothermal vents, didn't just survive in Earth's harsh conditions, they began reshaping the planet itself. Cyanobacteria, harnessing sunlight through photosynthesis, started pumping oxygen into the atmosphere as a waste product. Over hundreds of millions of years, this oxygen built up, triggering what scientists call the Great Oxygenation Event, a planetary revolution that wiped out many early life forms but paved the way for more complex organisms. Earth's transformation didn't stop there. Plate tectonics, the slow dance of continental drift, began sculpting the planet's surface, creating mountains, valleys, and new habitats. Ice ages came and went. Asteroid impacts caused mass extinctions, and yet life persisted, adapting and evolving through every catastrophe. The rise of multicellular organisms, the explosion of biodiversity during the Cambrian period, the colonization of land, each milestone was a testament to life's incredible resilience and ingenuity. What's truly humbling is how delicate this balance was. If Earth had been slightly closer to the Sun, its oceans might have evaporated. Without the Moon's stabilizing influence, its axis could have wobbled wildly, creating extreme climate swings. Even the asteroid impacts that caused mass extinctions played a role, clearing the way for new life forms to dominate. Every element, from the composition of the atmosphere to the salinity of the seas, had to align just right for complex life to flourish. Today, when we look at our planet's vibrant biosphere, we're seeing the result of 4.5 billion years of cosmic fine-tuning. The same forces that shaped Earth geology, chemistry, biology are at work right now, continuing to remake the world beneath our feet. And as we search for life beyond our solar system, Earth's story reminds us that even in the vast, indifferent universe, the right conditions can turn a ball of molten rock into a living, breathing world. The story of our moon begins with violence, a cataclysm so immense it reshaped Earth's destiny. Picture the early solar system, still cluttered with debris when a rogue planetoid the size of Mars, now called Theia, drifted too close to our young planet. The collision wasn't a gentle nudge, it was a head-on smash at thousands of kilometers per hour, so powerful it vaporized part of Earth's crust and sent molten rock splashing into space. The energy released would have turned Earth's surface into a global ocean of magma, while debris from both worlds formed a glowing ring around our planet, like Saturn's rings but made of fire. What happened next was cosmic alchemy. Within just a few centuries, gravity sculpted that debris into a single, molten sphere, our moon. But this newborn satellite was far closer than today, looming so large in the sky it would have appeared 15 times bigger than the modern moon. Over billions of years, tidal forces pushed it outward to its current orbit, leaving behind subtle fingerprints like the slowing of Earth's rotation. Our days growing longer as the moon stole energy from our spin. The moon's greatest gift wasn't just its presence, it was stability. Earth's axial tilt, which gives us seasons, wobbles naturally over time. Without the moon's gravitational anchor, our planet might have tipped wildly, causing climate swings so extreme that complex life could never have gained a foothold. Mars, with its puny moons, experiences tilt variations of up to 60 degrees, enough to turn polar ice caps into tropical jungles over millennia. Earth's tilt, by contrast, has stayed within a narrow, life-friendly range of just 22 to 24.5 degrees, all thanks to our lunar guardian. Yet the moon's influence runs deeper. Its tides helped stir Earth's early oceans, possibly aiding the chemical reactions that led to life. Some scientists even suggest the moon's gravitational pull may have helped maintain Earth's magnetic field by stirring molten iron in our core, a planetary shield against deadly solar radiation. And let's not forget its role as a cosmic timekeeper, with lunar cycles guiding the rhythms of countless species, from coral reproduction to human agriculture. Theia's collision left another curious legacy. Moon rocks brought back by Apollo astronauts contain isotopes nearly identical to Earth's. a clue that the impacting body mixed thoroughly with our planet's material. If Theia had struck at a different angle or speed, we might have ended up with multiple moons or none at all. Instead, we got a singular companion whose quiet presence has quietly shaped every chapter of Earth's story. So when you gaze at the moon tonight, remember, you're not just looking at a rocky satellite. You're seeing the aftermath of the solar system's most consequential car crash, a celestial partner whose gravitational embrace made Earth the stable, life-rich world it is today. Without that ancient catastrophe, the night sky would be empty, the tides would be feeble, and the chances of you standing here to ponder it all would be vanishingly small. The moon is more than Earth's child, it's the silent architect of our existence. Our sun isn't just another star, it's the ultimate cosmic guardian, a steady beacon in a universe filled with stellar extremes. While massive stars blaze through their fuel in mere millions of years, our sun's modest size grants it a lifespan stretching over 10 billion years, a longevity that's been essential for life's slow, delicate evolution here on Earth. Right now, it's comfortably middle-aged, about 4.6 billion years into its journey, with another 5 billion still to go. But what makes it so perfectly suited to nurture life? For starters, the sun's size is just right, not too small to be a dim, cool red dwarf, and not so large that it would scorch nearby planets with lethal radiation. Its surface temperature hovers around 5,500 degrees Celsius, emitting a balanced spectrum of light that plants evolved to harness through photosynthesis. Imagine if our star were slightly hotter or cooler. Even a 10% change could have made Earth either a frozen wasteland or a scorched desert. The sun's stability is equally crucial. Unlike volatile young stars that unleash violent flares, our sun's activity follows a relatively predictable 11-year cycle, with sunspots and solar storms rarely intense enough to disrupt life's rhythms. Yet this stability isn't permanent. Deep in its core, the sun fuses 600 million tons of hydrogen into helium every second, a process that's gradually altering its composition. As hydrogen dwindles, the core contracts, heating up and pushing the sun's outer layers outward. In about 5 billion years, it will swell into a red giant, its surface expanding beyond the orbit of Mercury, then Venus, and possibly even Earth. The once life-giving star will transform into a planetary devourer, its intense heat boiling away oceans and stripping atmospheres. But here's the twist: long before that fiery end, the sun's slow brightening will make Earth uninhabitable. In just 1 billion years, increased solar radiation will trigger a runaway greenhouse effect, turning our planet into a second Venus long before the red giant phase begins. This timeline might sound grim, but it underscores how precious and fleeting our window of habitability truly is. What's often overlooked is how rare a star like our sun really is. Red dwarfs, the most common stars in the galaxy, are prone to deadly flares and tidal lock their planets, leaving one side perpetually scorched and the other frozen. Giant stars die too quickly for complex life to emerge. Our sun sits in a stellar sweet spot, its quiet reliability allowing life the time and conditions it needed to flourish. So when you feel the sun's warmth on your skin, remember, you're basking in the glow of a cosmic Goldilocks star, one whose age, size, and temperament aligned perfectly to turn a rocky planet into a living world. Its constancy is an illusion, though a temporary gift in an ever-changing universe, reminding us that even the stars that light our skies are bound by time. For centuries, humans gazed at the stars and wondered, are there other worlds out there, or is Earth alone in its cosmic solitude? That question was finally answered in 1992, when astronomers detected the first confirmed exoplanets orbiting a pulsar nearly 2,300 light-years away. Since then, the floodgates have opened. We've discovered over 5,000 exoplanets, with estimates suggesting hundreds of billions more may exist in our galaxy alone. These aren't just distant dots on a telescope sensor their entire worlds, some with oceans of molten lava, others with skies raining glass, and a precious few that might just resemble the pale blue dot we call home. Take the TRAPPIST-1 system, for example, a cosmic neighbor just 40 light-years away with 7 Earth-sized planets, 3 of which sit snugly in the habitable zone where liquid water could exist. Or consider Kepler 452b, a world dubbed Earth's cousin, orbiting a sun-like star at the perfect distance for temperate conditions. But perhaps most intriguing is Proxima Centauri b, the closest known exoplanet to us at a mere 4.2 light-years, where a rocky surface might bask under the dim glow of its red dwarf sun. Finding these worlds isn't easy. Unlike stars, planets don't emit their own light, they're cosmic burglars, revealing themselves only through subtle tricks. The transit method watches for a star's dimming as a planet crosses its face, while radial velocity detects a star's wobble caused by an orbiting planet's gravitational tug. More recently, direct imaging has captured a handful of exoplanets as faint specks next to their brilliant parent stars, like spotting a firefly near a searchlight. What's truly revolutionary is how diverse these worlds are. Hot Jupiter's gas giants roasting close to their stars defy our solar system's orderly architecture. Super-Earths, larger than our planet but smaller than Neptune, challenge our understanding of rocky worlds. Then there's HD 189733b, where winds scream at 7,000 kilometers per hour, carrying vaporized glass sideways in its scorching atmosphere. Or WASP 76b, where iron rains from the sky at night, condensing on the planet's cooler dark side. Yet amid this cosmic menagerie, the Holy Grail remains, an Earth twin, a world not just the right size and temperature, but one with the right chemistry for life as we know it. The James Webb Space Telescope is now peering into exoplanet atmospheres, hunting for biosignatures, oxygen, methane, or other gases that might hint at biological activity. A single whiff of these gases in the right combination could rewrite humanity's place in the universe. Every new exoplanet discovery carries a dual revelation. Some remind us how strange and varied planets can be, while others whisper that Earth might not be so unique after all. Whether we're alone in the universe isn't just a philosophical question anymore. It's a scientific one, and the answer might be hiding in the dim light of a distant world's atmosphere, waiting for us to decode its secrets. The hunt for life beyond Earth isn't just science fiction anymore, it's a meticulous scientific pursuit unfolding right now across our solar system and beyond. Picture astronomers peering through the James Webb Space Telescope, analyzing the faint starlight filtering through distant exoplanet atmospheres, searching for chemical imbalances that could only be explained by living organisms. Oxygen and methane, when found together, are particularly tantalizing on Earth. Their coexistence is a clear signature of life, since these gases react quickly and shouldn't persist unless something is constantly replenishing them. But the challenge is staggering. Detecting these whispers of biology across light years requires instruments so sensitive they can spot a single candle flickering on the moon. Meanwhile, much closer to home, robotic explorers are scouring Mars for signs of ancient or even present-day microbes. The Perseverance rover isn't just driving across the red planet, it's collecting samples that might contain fossilized bacteria from a time when Mars had rivers and lakes. Underground, where radiation can't reach, there could still be pockets of liquid water, warm enough for extremophile organisms like those thriving in Earth's most hostile environments. And then there's Europa, Jupiter's icy moon, hiding a global ocean beneath its frozen crust. Tidal forces from Jupiter's gravity keep this subsurface sea liquid, and plumes of water vapor erupting from its surface hint at hydrothermal vents, the very places where life might have started on Earth. But why does finding even the simplest extraterrestrial life matter so much? Because it would rewrite the rules of biology. Every living thing we know shares the same basic DNA blueprint, suggesting a single origin. If life arose independently elsewhere, it would prove that biology isn't a fluke, it's a cosmic imperative, likely scattered across countless worlds. The implications are staggering. Life could be as common as stars, evolving wherever conditions allow. Or if our searches come up empty despite decades of effort, we might confront an eerie possibility that life, at least as we know it, is vanishingly rare, and Earth is a lone oasis in a sterile universe. This search isn't just about microbes or chemical signatures. It's about answering humanity's oldest question: are we alone? The discovery of even a single alien bacterium would shatter our cosmic solitude, proving that life isn't just an earthly accident but a fundamental feature of the universe. Until then, every rover rolling across Martian soil, every telescope dissecting exoplanet atmospheres, brings us one step closer to knowing whether we're the universe's only children or just one voice in a galactic chorus of life. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out with a bang so powerful it can outshine entire galaxies for weeks. This is a supernova, the universe's ultimate fireworks show and one of nature's most extraordinary element factories. Picture a star 20 times more massive than our Sun, its core burning through nuclear fuel at a breakneck pace. For millions of years, it fuses lighter elements into heavier ones, hydrogen to helium, helium to carbon, and so on, until its core becomes a ticking time bomb of iron. Iron is different. Unlike previous elements, fusing it doesn't release energy, it sucks energy in, starving the star of its power source. In seconds, the core collapses under its own gravity, triggering an explosion so violent it flings the star's outer layers into space at nearly 10% the speed of light. The aftermath is where the magic happens. The extreme temperatures and pressures in those expanding shockwaves forge elements heavier than iron, gold, platinum, uranium, that ordinary stellar fusion could never create. These newly minted atoms are catapulted into the cosmos, seeding future generations of stars and planets with the raw materials for everything from mountain ranges to microchips. In fact, the gold in your jewelry or the uranium fueling nuclear reactors was born in the heart of a dying star billions of years ago. Without supernova, the periodic table would stop at iron, and life as we know it wouldn't exist. But the star's core isn't finished yet. Depending on its mass, it can collapse into one of two cosmic oddities, a neutron star or a black hole. Neutron stars are so dense that a single sugar cube-sized chunk would weigh as much as Mount Everest. They spin at dizzying speeds, some whirling hundreds of times per second, while others, called magnetars, possess magnetic fields trillions of times stronger than Earth. Then there are black holes, gravity's ultimate victory, where matter is crushed into a point so small and dense that not even light can escape. Supernovae aren't just destructive, they're creative forces. Their shockwaves compress nearby gas clouds, triggering the birth of new stars and planetary systems. Our own solar system might owe its existence to a long ago supernova's disruptive influence. Even today, these explosions continue to shape the galaxy, recycling stellar material and enriching the cosmos with the building blocks of planets, life, and even consciousness. So the next time you look up at the night sky, remember, you're made of stardust, but not just any stardust. You're made of the ashes of cosmic giants that died so you could exist. Neutron stars are nature's ultimate paradox, stellar corpses so dense they defy common sense. Picture squeezing the entire mass of our sun into a sphere no wider than Manhattan, where gravity is strong enough to bend light into a visible halo around it. A single teaspoon of neutron star material wouldn't just weigh 1 billion tons, it would crush you under its own gravity long before you could lift it. Yet these cosmic oddities aren't just curiosities, they're extreme laboratories pushing the boundaries of physics in ways no experiment on Earth ever could. Among neutron stars, pulsars stand out as the universe's precision timekeepers. Born from the violent death throes of massive stars, these rapidly spinning remnants emit beams of radiation, radio waves, X-rays, even gamma rays from their magnetic poles. Like a lighthouse beam sweeping across a dark sea, these pulses flash toward Earth with metronomic regularity, some ticking with a stability that rivals atomic clocks. The Crab pulsar, the remnant of a supernova observed in 1054, spins 30 times per second, its beams flickering with such predictability you could set your watch by them. But pulsars aren't just cosmic beacons, they're also gravity probes. When two pulsars orbit each other, as in the famous Hulse-Taylor binary system, their dance emits gravitational waves, ripples in space-time predicted by Einstein and later confirmed by observatories like LIGO. These pairs act as natural testbeds for general relativity, allowing scientists to scrutinize gravity's behavior under conditions impossible to replicate in any lab. The precision of their pulses even helped astronomers indirectly confirm the existence of gravitational waves decades before direct detection. Then there are magnetars, neutron stars with magnetic fields so intense they could erase a credit card from halfway across the solar system. These cosmic powerhouses occasionally release starquakes, sudden fractures in their rigid crusts that unleash bursts of gamma rays visible across the universe. In 2004, a magnetar flare from 50,000 light-years away briefly outshone the full moon, despite being far beyond our galaxy's edge. What makes neutron stars truly remarkable is how they bridge the gap between the familiar and the unfathomable. Their surface gravity is strong enough to squash atoms into a bizarre quantum soup, while their cores might contain exotic states of matter, free quarks or hyperons that could rewrite our understanding of particle physics. Some theories even suggest they could harbor strange stars, made not of neutrons but of strange quark matter, a substance so stable it could be the true endpoint of stellar collapse. Yet for all their ferocity, neutron stars play a quiet but crucial role in the cosmos. Their collisions seed galaxies with heavy elements like gold and platinum. Their gravity sculpts star clusters, and their pulses serve as galactic mile markers for future interstellar navigation. They remind us that even in death, stars continue to shape the universe not just as relics, but as active participants in the grand story of cosmic evolution. So the next time you hear the steady tick of a pulsar's signal, remember, you're listening to the heartbeat of a stellar giant, reduced to a city-sized diamond spinning in the dark. Black holes bend the very fabric of reality in ways that challenge our understanding of physics. Imagine standing near one, though your feet would be shredded by tidal forces long before you got close, and witnessing time distort like taffy. Clocks tick slower the deeper you descend into a black hole's gravitational well, an effect predicted by Einstein's theory of relativity. Near the event horizon, that invisible boundary where even light can't escape, time would crawl so agonizingly slow that while mere minutes passed for you, centuries could unfold for the rest of the universe. It's a one-way trip into a cosmic time machine where the laws of physics as we know them cease to apply. Yet black holes aren't just destructive, they're also creative engines. Quasars, the brightest objects in the universe, are powered by supermassive black holes devouring entire stars. As matter spirals into these gravitational monsters at nearly light speed, friction heats it to millions of degrees, creating jets of energy that can outshine galaxies. These beams, stretching thousands of light years into space, act like interstellar blowtorches, carving out bubbles in surrounding gas clouds and influencing star formation across cosmic distances. Without black holes stirring the galactic pot, the universe might lack the turbulence needed to birth new stars and planets. What's truly bizarre is how black holes defy our classical notions of space and matter. Inside, all the information about what fell in whether stars, planets, or spacecraft gets crushed into a single point of infinite density called a singularity. Here, space and time twist so severely that the very concepts of before and after lose meaning. Some theories suggest singularities might be gateways to other universes or dimensions, though we've yet to find evidence. What we do know is that black holes slowly evaporate over eons, leaking energy via Hawking radiation, a quantum quirk that ensures even these cosmic titans aren't eternal. Studying black holes isn't just about unraveling their mysteries, it's a window into the universe's fate. The way they warp space-time offers clues about dark energy, the force accelerating cosmic expansion. Their collisions, detected through gravitational waves, reveal how galaxies merge and grow. Even their shadows, like the iconic image of M87's black hole, test relativity's limits under extreme conditions. Every discovery peels back another layer, showing us that black holes aren't just in points, they're active players in shaping the cosmos, bending the rules of existence itself to forge the universe we see today. Dark matter is the universe's greatest ghost story, an invisible presence that shapes everything we see, yet refuses to reveal itself. Think of it like the wind. You can't see it, but you feel its effects everywhere. Galaxies spin so fast they should tear themselves apart, yet something unseen holds them together. Clusters of galaxies move in ways that defy the gravity of visible matter alone. The culprit, a mysterious substance that doesn't emit, absorb, or reflect light, dark matter, making up roughly 27% of the cosmos. Without it, the universe as we know it wouldn't exist. The evidence for dark matter isn't just compelling, it's everywhere. Take spiral galaxies, for example. Their outer stars orbit so quickly that the visible mass of stars and gas couldn't possibly keep them from flying off into space. It's like watching a carousel spin with no one holding the reins, yet somehow the riders stay firmly in place. The only explanation, an enormous halo of invisible matter, its gravity acting like cosmic glue. Even more striking are galaxy clusters, where the gravitational tug of unseen material bends light from background galaxies, a phenomenon called gravitational lensing. These cosmic magnifying glasses reveal dark matter's fingerprints, warping spacetime itself. So what is dark matter? The leading theory suggests it's a new kind of particle, one that barely interacts with normal matter except through gravity. Scientists call these hypothetical particles WIMP, weakly interacting massive particles, and experiment's deep underground hunt for their elusive signals. But there's a twist. Decades of searching have turned up nothing, leading some to question if we're chasing a phantom. Alternative theories propose that gravity itself behaves differently on cosmic scales, a concept called modified Newtonian dynamics, or MN. Yet even MN struggles to explain all the observations, leaving dark matter as the most plausible explanation for now. The stakes couldn't be higher. If dark matter is a particle, it would mean the standard model of physics is incomplete, a revelation as profound as the discovery of the Higgs boson. If it's a quirk of gravity, Einstein's theory of relativity might need rewriting. Either way, solving this mystery could unlock secrets about the universe's birth, evolution, and ultimate fate. One thing's certain, dark matter isn't just a scientific curiosity. It's the scaffolding upon which galaxies are built. Without it, stars would never have clumped together into the majestic spirals and clusters we see today. It's the silent architect of the cosmos, weaving the structures that make life possible, even as it remains forever hidden in the shadows. The hunt for dark matter isn't just about finding a missing piece of the puzzle. It's about understanding the very blueprint of reality. If dark matter is the universe's invisible scaffolding, dark energy is its mysterious engine, a force so perplexing it makes galaxies flee from one another at ever-increasing speeds. Picture this: in the late 1990s, two teams of astronomers were observing distant supernovae, expecting to confirm the long-held assumption that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. These exploding stars were fainter and thus farther away than they should have been, revealing a shocking truth. The cosmos isn't just expanding, it's accelerating, as if some unseen hand is pressing harder on the cosmic gas pedal with each passing moment. This discovery, which earned the Nobel Prize in 2011, upended everything we thought we knew about cosmic fate. The culprit, dark energy, an enigmatic phenomenon making up roughly 68% of the universe's total energy budget. Unlike dark matter, which pulls galaxies together through gravity, dark energy appears to push space itself apart. Imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move away from each other. Now picture someone suddenly inflating that balloon faster and faster for no apparent reason. That's the puzzle astronomers are grappling with. What makes dark energy so baffling is how little we understand it. The leading theory suggests it's a property of space itself, what Einstein once called the cosmological constant, a kind of energy inherent to the vacuum of space. But there's a problem. When physicists calculate how strong this energy should be based on quantum mechanics, the predicted value is staggeringly larger than what we observe. It's like expecting a tidal wave and getting a ripple instead. Other theories propose that dark energy might be a dynamic field, evolving over time, or even evidence of extra dimensions lurking beyond our perception. The implications are staggering. If dark energy remains dominant, the universe will continue expanding faster and faster, eventually pulling galaxies so far apart that their light can never reach us. Distant civilizations billions of years from now might look up at an empty sky, their universe reduced to a solitary island of stars. But if dark energy weakens or changes over time, the cosmos could face a big rip, where even atoms are torn apart, or a big crunch, collapsing back into a singularity. Here's the twist: dark energy's discovery was only possible because of tools like the Hubble Space Telescope and painstaking observations of supernovae. Today, instruments like the Dark Energy Survey and the upcoming Euclid spacecraft are mapping millions of galaxies to trace how dark energy has shaped cosmic history. Each new dataset is a clue in this grand detective story, one that could rewrite our understanding of physics itself. So while dark energy remains invisible, its fingerprints are everywhere, stretching the fabric of space, dictating the universe's fate, and reminding us that the cosmos is far stranger than we ever imagined. The mystery isn't just academic. It's a race to understand whether we live in a universe destined for eternal expansion or one that might someday collapse back into darkness. And in that answer lies the ultimate fate of everything we know. The cosmos isn't a random splatter of galaxies, it's a meticulously woven tapestry, a sprawling network of luminous threads and yawning voids known as the cosmic web. Picture the universe's largest structures not as isolated islands, but as interconnected cities linked by highways of dark matter and gas, stretching across billions of light years. These filaments, some as long as 500 million light years, form the backbone of the universe's architecture, with galaxy clusters glittering like pearls at their intersections. Between them lie the voids, immense, nearly empty regions so vast they could swallow thousands of Milky Ways without a trace. This isn't chaos, it's gravity's masterpiece, painted over 13 billion years of cosmic evolution. How did this intricate web emerge? The story begins with the faintest ripples in the early universe, tiny density fluctuations imprinted in the cosmic microwave background. Over eons, gravity amplified these ripples, pulling matter into denser regions while emptying others. Dark matter, invisible and mysterious, led the charge. Its gravity sculpted the filaments, while ordinary gas and galaxies followed like iron filings drawn to a magnet. Supercomputer simulations reveal this process in stunning detail. Dark matter's tendrils form first, a ghostly skeleton, with visible matter later condensing along these lines like dew on a spider's web. The result, a universe structured like a sponge, with galaxies strung along filaments and clusters, marking the spots where those filaments intersect. What's truly mind-bending is the scale. The Sloan Great Wall, one of the largest known structures, spans over 1.4 billion light-years, a filament so enormous it challenges our understanding of cosmic homogeneity. Yet even this pales next to the Hercules Corona Borealis Great Wall, a galactic superstructure stretching 10 billion light-years, a relic from when the universe was half its current age. These aren't just curiosities, they're critical clues. The cosmic web's pattern holds secrets about dark energy's influence, the universe's expansion rate, and even the nature of gravity itself. But here's the twist. We're not just observers of this web, we're embedded in it. The Milky Way resides in the Laniakea supercluster, a filamentary structure 150 million light-years wide, with thousands of galaxies flowing toward a gravitational focal point called the Great Attractor. Our local universe is in motion, carried along these cosmic currents like a leaf in a river. And just as rivers shape landscapes, these filaments shape galaxies. Gas streaming along them fuels star formation, while voids act as deserts, starving galaxies of new material. The cosmic web isn't static. It's a dynamic, evolving entity, with galaxies tugged into clusters and superclusters in an endless gravitational dance. The cosmic web reminds us that the universe is anything but random. From the tiniest quantum fluctuations to the grandest superclusters, everything is connected. A reminder that even in the vastness of space, we're part of something far greater than ourselves. What if our universe isn't the only one? Imagine a cosmic library where each book contains an entirely different reality, some with stronger gravity, others where light moves slower, or where life as we know it could never exist. This isn't science fiction, it's the multiverse theory, a radical idea gaining traction among physicists. While we can't yet prove other universes exist, the math behind quantum mechanics and cosmic inflation suggests our reality might be just one bubble in an endless froth of parallel worlds. The concept emerges from two surprising corners of modern physics. First, quantum mechanics tells us particles exist in multiple states until observed, a phenomenon called superposition. Some interpretations suggest every possible outcome does happen, but in separate, branching universes. Then there's eternal inflation, the idea that space-time expands exponentially in some regions while new, pocket universes bud off with unique physics. Like bubbles forming in boiling water, Each universe could have different fundamental constants, and perhaps some where stars never ignite or others where matter is impossibly unstable. String theory, a framework attempting to unify all physical forces, adds another layer. It proposes our universe's laws depend on how tiny, vibrating strings of energy are configured. But math suggests there could be 10 to the power of 500 possible configurations, meaning there might be more potential universes than particles in our own. Some physicists argue this landscape of possibilities isn't just theoretical. If even a fraction exists, it would explain why our universe seems finely tuned for life. After all, in an infinite multiverse, some universe had to get lucky. Critics dismiss the multiverse as untestable speculation, but supporters point to tantalizing clues. Strange cold spots in the cosmic microwave background could be bruises from collisions with other universes. The inexplicably low energy of our vacuum state might hint at neighboring realities tugging on ours. Future telescopes mapping the universe's curvature could even reveal a telltale pattern, evidence we're part of a larger multiversal structure. Whether the multiverse is real or not, the idea reshapes our cosmic perspective. If true, it means every choice you've ever made spawned alternate versions of yourself living different lives in parallel worlds. More profoundly, it suggests our universe's laws aren't special, just one possible outcome in a grand, perhaps infinite, cosmic experiment. Until we find proof, the multiverse remains a thrilling frontier, one that challenges us to rethink not just where we are, but what we are in the grand scheme of existence. The universe's ultimate fate hinges on a silent tug of war between gravity's pull and dark energies push, a battle that will play out over trillions of years. Picture two possible endings, each more dramatic than the last. In one scenario, dark energy's relentless acceleration never stops, forcing galaxies to drift apart until every star burns out, every black hole evaporates, and the cosmos becomes a vast, icy graveyard where not even atoms move. This is heat death, not a fiery explosion, but a slow, chilling fade into darkness, where the universe's temperature approaches absolute zero and time itself loses all meaning. It's a poetic yet haunting finale where even the memory of light is swallowed by endless expansion. But there's another possibility, one where dark energy weakens over time, allowing gravity to finally take the upper hand. Galaxies, then stars, then atoms themselves could reverse their outward flight, collapsing back into a single point of infinite density, the Big Crunch. Imagine all of existence hurtling toward a fiery reunion, space and time crumpling like a sheet of paper tossed into a flame. Some theories suggest this singularity might even trigger another Big Bang, birthing a brand new universe in an endless cycle of destruction and rebirth. The idea of a cyclical cosmos isn't just philosophical, it's rooted in models of string theory and bouncing cosmology, where each iteration tweaks the laws of physics slightly, creating a multiverse of trial and error realities. Then there's vacuum decay, perhaps the most unsettling endgame of all. Quantum physics suggests our universe might exist in a false vacuum state, a precarious balance that could, at any moment, collapse into a more stable configuration. If this happened, a bubble of true vacuum would expand at the speed of light, rewriting the fundamental constants of nature as it goes. Atoms would disintegrate, forces would unravel, and the universe as we know it would cease to exist in an instant, not with a bang or a whimper, but with a silent, irreversible rewrite of reality itself. These scenarios aren't just thought experiments, they're windows into the deepest laws of nature. The way the universe ends depends on mysteries we're still unraveling, the true nature of dark energy, the stability of the quantum vacuum, even the shape of space-time itself. What's striking isn't just the scale of these finales, but their inevitability. Whether it's heat death's endless night or the Big Crunch's fiery rebirth, the cosmos reminds us that nothing lasts forever, not even existence itself. Yet in that impermanence lies a strange comfort. Every star that dies, every galaxy that fades, is part of a story far grander than we can comprehend, one where endings are just preludes to whatever comes next. Time isn't the rigid, unchanging river we perceive. It's more like a stretchy fabric, warped and woven by gravity and motion. Einstein's theory of relativity revealed this startling truth. Clocks tick slower near massive objects like black holes or when racing at near light speeds. Imagine twin astronauts. One stays on Earth while the other rockets away at 90% light speed. Upon return, the traveling twin would be younger, their personal timeline stretched compared to their siblings. This isn't science fiction. It's been confirmed by atomic clocks on fast-moving jets and satellites in orbit. But if time can bend, could it fold back on itself? Could we build a cosmic shortcut to the past or future? The math suggests tantalizing possibilities. Wormholes, hypothetical tunnels through space-time, could, in theory, connect distant moments as easily as distant places. Picture a black hole's crushing gravity linked to a white hole's explosive outflow, forming a bridge across time. Or cosmic strings, infinitely thin threads of primordial energy left over from the Big Bang, whose immense gravitational fields might warp time into loops. Even rotating black holes, like the one depicted in Interstellar, could twist space-time so severely that entering their ergosphere might offer a path to another era. The equations allow it, but nature often has other plans. Here's the catch: stability and paradoxes. Wormholes would likely collapse instantly unless propped open by exotic matter with negative energy, a substance we've never observed. Cosmic strings, if they exist, are thinner than an atom and might require the mass of entire stars to bend time meaningfully. And then there's the infamous grandfather paradox. If you traveled back and prevented your own birth, how could you exist to time travel in the first place? Some physicists propose parallel timelines or self-correcting events to sidestep this, but these ideas remain untested. Yet the dream persists, driving real science. Researchers at CERN monitor particle collisions for microscopic time loops. Quantum experiments explore closed time-like curves where particles might influence their own past. Even NASA has funded studies on warp drives, inspired by physicist Miguel Alcubierre's model for faster-than-light travel, a concept that, while speculative, keeps the imaginative door ajar. Time travel captivates because it touches the core of human longing to undo regrets, witness history, or glimpse the future. While we're far from building a TARDIS, the universe whispers that the past and future might not be as distant as they seem. For now, the best time machine we have is a telescope, peering at light that's traveled billions of years to show us the universe's youth, but who knows? The cosmos has surprised us before. Crossing the cosmic void between stars isn't just a challenge, it's a test of human ingenuity against the universe's harshest realities. Take Alpha Centauri, our closest stellar neighbor at 4.3 light-years away. At the speed of New Horizons, the fastest spacecraft we've ever launched, that journey would take nearly 70,000 years, longer than all recorded human history. Yet the dream persists, fueled by concepts that sound like science fiction but are rooted in real physics. Consider the light sail, where a spacecraft unfurls a giant reflective sheet to catch the momentum of photons from powerful ground-based lasers. The Breakthrough Starshot initiative envisions tiny probes accelerated to 20% light speed this way, reaching Alpha Centauri in just 20 years. These wafer-thin crafts would carry cameras and sensors, beaming back our first close-up images of another star system. but the engineering hurdles are staggering, maintaining laser focus across astronomical distances, shielding the probes from interstellar dust impacts, and developing power sources that last decades in the freezing void. Then there's the warp drive, inspired by Einstein's equations showing spacetime can bend. By compressing space in front of a ship while expanding it behind, theorists suggest faster-than-light travel might be possible without breaking relativity, creating a bubble of warped spacetime that carries the vessel along. The catch: it would require exotic matter with negative energy density, something we've never observed naturally. Recent calculations show even a microscopic warp bubble would need the energy equivalent of Jupiter's mass, though some scientists speculate quantum-scale versions might one day be feasible. For missions carrying humans, generation ships present another possibility: self-sustaining arcs, where multiple generations live and die during centuries-long voyages. These would require closed ecosystems rivaling Earth's complexity, along with solutions for radiation shielding, artificial gravity through rotation, and psychological stability for crews born into deep space. The challenges are immense, but studies of isolated communities on Earth and the International Space Station offer clues about how humans might adapt to such journeys. The cold truth is that interstellar travel pushes against fundamental limits, not just technological, but biological and economic. Yet history shows humanity's knack for turning impossibilities into milestones. 500 years ago, crossing oceans took months with high mortality rates. Today, we do it in hours. The stars may remain out of reach for now, but each theoretical breakthrough and tiny robotic probe brings them incrementally closer. The universe has given us a cosmic shoreline to gaze upon, and one day, perhaps, to sail beyond. The silence of the cosmos is one of its greatest mysteries. With hundreds of billions of galaxies, each containing billions of stars and planets, the universe should be teeming with civilizations, yet we've found no definitive proof of anyone else out there. This contradiction is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is common, why hasn't it announced itself?" The answers we've come up with range from sobering to downright chilling. One possibility is that life is extraordinarily rare. Even in a universe brimming with planets, the leap from chemistry to biology might require such a precise cocktail of conditions that Earth is a cosmic fluke. Think of it like rolling a million-sided die and landing on the same number twice possible, but staggeringly unlikely. Or perhaps life emerges often, but intelligence is the bottleneck. Dinosaurs ruled Earth for over 100 million years without ever developing radio telescopes or spaceflight. What if most life gets stuck in a perpetual state of primal competition, never reaching the technological stage needed to broadcast its existence? Then there's the darker scenarios. Advanced civilizations might inevitably face existential threats: nuclear war, runaway AI, climate collapse, and wipe themselves out before they can colonize the stars. This great filter hypothesis suggests that the reason we don't see aliens is because they all hit a wall we haven't encountered yet. The unsettling question is whether that wall lies ahead of us or behind us. But not all explanations are so bleak. Maybe we're just looking in the wrong way. SETI, the search for extraterrestrial intelligence, has spent decades scanning for radio signals, but an advanced civilization might communicate using neutrinos, gravitational waves, or something we haven't even imagined. It's like trying to find a smartphone in ancient Rome by listening for ringtones. The technology gap is too vast. Others propose that aliens might be deliberately avoiding us, either to let us develop undisturbed or because we're not yet interesting enough to contact. The truth is, we're still at the very beginning of this search. with new telescopes like the James Webb peering into exoplanet atmospheres and projects like Breakthrough listen scanning millions of stars, we might be on the verge of an answer. Until then, the Fermi Paradox remains both a humbling reminder of our cosmic loneliness and an open invitation to keep exploring. The universe has whispered its secrets for billions of years. We're only just learning how to listen. Astrobiology doesn't just ask whether life exists beyond Earth. It rewrites the very definition of what life could be. Imagine organisms thriving in sulfuric acid clouds, microbes buried under kilometers of Antarctic ice, or bacteria surviving the vacuum of space. These extremophiles, Earth's most resilient life forms, are the cornerstone of astrobiology, proving that life can persist in conditions once thought utterly inhospitable. Take Deinococcus radiodurans, a bacterium capable of withstanding radiation doses thousands of times stronger than what would kill a human, or tardigrades, microscopic water bears that can enter a state of suspended animation, surviving extreme heat, cold, and even the crushing pressures of the deep sea. If life can flourish in such punishing environments on Earth, why couldn't it adapt to the icy oceans of Europa or the methane lakes of Titan? The search for extraterrestrial life begins with chemistry. Astrobiologists study prebiotic molecules, the building blocks of life found in meteorites, interstellar clouds, and even the atmospheres of distant planets. The discovery of amino acids in the Murchison meteorite or phosphine in Venus's clouds sparks debates. Are these signatures of unknown geological processes or faint whispers of biology? The line between chemistry and life blurs in places like hydrothermal vents, where scorching mineral-rich water fuels entire ecosystems without sunlight. These vents, teeming with tube worms and bacteria, offer a blueprint for how life might arise on ocean worlds like Enceladus, where geysers spew water into space from a hidden sea. Mars remains astrobiology's most tantalizing target. Billions of years ago, it had rivers, lakes, and possibly even a northern ocean. Today, rovers like Perseverance scour Jezero Crater, an ancient lakebed, for fossils of microbial mats that might have thrived when Mars was wet. Underground, where radiation can't reach, liquid water might still persist, hosting bacteria akin to Earth's deep subsurface microbes. Even more intriguing are the seasonal methane plumes detected by orbiters, a gas often produced by living organisms, though geological reactions can't be ruled out. Mars teaches us that life, if it ever existed there, might not be extinct just hiding, waiting to be found beneath the rust-colored soil. But astrobiology's scope stretches far beyond our solar system. Exoplanets like K2-18b, a Hycean world with water vapor in its atmosphere, or TRAPPIST-1e, a rocky planet in the habitable zone of a cool dwarf star, are prime candidates for biosignature searches. The James Webb Space Telescope is analyzing the chemical makeup of these distant atmospheres, hunting for imbalances like oxygen and methane coexisting that could only be explained by life. The challenge: distinguishing biological signals from false positives. A planet's geology, star activity, or even cosmic rays can mimic signs of life, turning the search into a cosmic detective story where every clue must be scrutinized. Perhaps the most profound shift astrobiology brings is philosophical. If life emerges wherever conditions allow, the universe could be a living, breathing tapestry. Conversely, if Earth remains the only example, we're forced to confront our extraordinary rarity. Either answer reshapes humanity's place in the cosmos. Astrobiology isn't just about finding aliens. It's about understanding life's resilience, its creativity, and its capacity to transform barren worlds into homes. Every new discovery, whether in a Martian rock or a distant exoplanet's atmosphere, doesn't just fill a textbook, it rewrites the story of existence itself. The universe is filled with puzzles that defy our understanding, mysteries so profound they challenge the very foundations of physics. Take dark matter, that invisible ghost holding galaxies together. We know it's there because of the way galaxies spin faster than visible matter can explain, and how light bends around galaxy clusters as if tugged by unseen hands. Yet after decades of searching, we still don't know what it's made of. Is it a yet undiscovered particle, a cosmic relic from the Big Bang, or could it be evidence that gravity itself behaves differently on cosmic scales? Underground labs hunt for dark matter particles with ultra-sensitive detectors, while telescopes map its distribution across the sky, hoping for a breakthrough. Until we solve this riddle, over 80% of the universe's matter remains hidden in plain sight. Then there's the mystery of matter's cosmic victory over antimatter. According to physics, the Big Bang should have created equal amounts of both, resulting in a universe that annihilated itself in a flash of energy. Yet here we are, in a world made almost entirely of matter. Where did all the antimatter go? Experiments at CERN study subtle differences in how matter and antimatter particles decay, searching for the asymmetry that tipped the scales. Some theories suggest antimatter might still exist in distant regions of the universe, forming entire anti-galaxies we've yet to detect. Others propose exotic processes in the early universe, like phase transitions or decaying heavy particles that favored matter's survival. Dark energy adds another layer to the cosmic puzzle. This mysterious force, driving the universe's accelerating expansion, behaves like anti-gravity, pushing galaxies apart with ever-increasing strength. Is it a property of space itself, as Einstein's cosmological constant suggested? Or is it a dynamic field that could change over time, altering the universe's fate? The answer could determine whether the cosmos ends in a frozen void or a fiery collapse. Even black holes, those gravitational monsters, hide enigmas. What happens inside the event horizon? Does information vanish forever, violating quantum mechanics, or is it somehow preserved? The recent detection of gravitational waves from colliding black holes has opened new ways to probe these questions, while theories like holography suggest the universe might encode information in ways we're only beginning to grasp. These aren't just academic curiosities, they're keys to understanding everything from the universe's birth to its ultimate fate. Each unsolved mystery represents a frontier where known physics breaks down, where new discoveries could rewrite the textbooks. And that's the thrill of cosmology. Every gap in our knowledge is an invitation to explore further, to push the boundaries of what we thought possible. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's what makes the search so exhilarating. The James Webb Space Telescope isn't just another observatory, it's a time machine revealing the universe's hidden chapters with unprecedented clarity. Unlike Hubble, which primarily sees visible light, Webb's infrared eyes pierce through cosmic dust, capturing wavelengths that have stretched over billions of years as the universe expanded. This lets it glimpse galaxies so distant their light has traveled over 13 billion years to reach us, showing us the cosmos when it was a mere infant. One of Webb's first deep-field images revealed galaxies from just 300 million years after the Big Bang toddlers in cosmic terms, already more mature than scientists predicted, forcing us to rethink how quickly the first stars and galaxies formed. But Webb's vision extends far beyond the early universe. Its spectrographs dissect the light from exoplanet atmospheres, identifying molecules like water vapor, carbon dioxide, and even potential biosignatures on worlds hundreds of light years away. Take K218b, a Hycean planet where we've detected methane and dimethyl sulfide, a compound on Earth only produced by life. While non-biological processes can't be ruled out yet, discoveries like this hint at the telescope's potential to one day answer humanity's oldest question: are we alone? Then there's Webb's ability to unravel stellar life cycles. Its images of the Carina Nebula and the Pillars of Creation show star-forming regions in breathtaking detail, with newborn stars blasting jets of material light years long. By studying these cosmic nurseries, Webb helps decode how stars are born, why some form planets, and how elements essential for life, like oxygen and carbon, are scattered across galaxies. Even dying stars get a closer look. Webb's observations of the Southern Ring Nebula exposed previously hidden binary star systems, proving that many planetary nebulae are sculpted by stellar duos, not single stars. Perhaps most astonishing is how Webb transforms abstract theories into tangible data. Dark matter's gravitational effects on galaxy shapes, now mapped with precision. The chaotic atmospheres of gas giants like Jupiter, revealed in swirling storms and auroras. Even the telescope's failures yield surprises. When it spotted galaxies supposedly too massive to exist so early in time, astrophysicists scrambled to adjust models of cosmic evolution. Webb's greatest gift isn't just the answers it provides, but the new questions it sparks. Every image, every spectrum, peels back another layer of the universe's mysteries, reminding us that exploration isn't about reaching an endpoint, it's about discovering how much more there is to explore. Einstein's theory of relativity painted a radical picture of the universe, one where space and time aren't just a static stage for cosmic events, but a dynamic fabric that can stretch, bend, and even ripple like the surface of a pond. For decades, gravitational waves, the faint tremors in this cosmic fabric, existed only as equations on paper. Then, in 2015, humanity finally heard the universe's hidden symphony. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal so subtle it required lasers measuring changes smaller than 1,000th the width of a proton. The source, two black holes, each about 30 times the mass of our Sun, spiraling toward each other at half the speed of light before colliding in a cataclysm so violent it shook spacetime itself, sending ripples across the cosmos that traveled for over 1 billion years before reaching Earth. This wasn't just a triumph of engineering, it was a revelation. For the first time, we weren't just seeing the universe through light, we were feeling its vibrations. Traditional telescopes show us snapshot stars flickering, galaxies spinning, but gravitational waves carry the soundtrack, the raw energy of cosmic collisions transcribed into waveforms. When neutron stars merge, they don't just emit gravitational ripples, they also produce gamma-ray bursts and scatter heavy elements like gold and platinum across space. By combining gravitational wave data with optical observations, scientists pieced together the origin of these precious metals, solving a mystery that had puzzled astronomers for decades. What makes gravitational waves so revolutionary is their ability to reveal the unseen. Black holes, by their very nature, emit no light, but when they collide, their gravitational waves scream across the universe. LIGO and its European counterpart, Virgo, have since detected dozens of these events, unveiling a population of black holes with masses that defy expectations. Some are too large to form from collapsing stars, suggesting they might be the remnants of earlier mergers. Others spin at dizzying rates, hinting at violent origins we're only beginning to understand. The future of this field is even more thrilling. New detectors, like the upcoming Laser Interferometer Space Antenna LISA, will float in space, free from Earth's seismic noise, to catch lower frequency waves from supermassive black holes merging at the hearts of galaxies. Others aim to listen for echoes from the Big Bang itself, primordial gravitational waves that could reveal the universe's first moments. Every detection peels back another layer of cosmic history, like an archaeologist uncovering fragments of a lost civilization. Gravitational waves remind us that the universe speaks in more than just light. It thrums with energy, pulses with collisions, and whispers secrets through the very fabric of space-time. With each ripple we capture, we're not just observers anymore, we're participants in a cosmic conversation that's been going on since the dawn of time. Consider the delicate balance of the universe's fundamental forces: gravity's pull, electromagnetism's grip, the nuclear forces binding atoms together. If any of these constants were tweaked by even a fraction, life as we know it would be impossible. Make gravity slightly stronger, and stars would burn out in millions of years instead of billions, leaving no time for evolution. Adjust the strong nuclear force by a hair, and carbon, the backbone of life's chemistry, might never form in stellar furnaces. This eerie precision isn't limited to physics. Even the universe's expansion rate appears fine-tuned. A faster early expansion would have scattered matter too thin for galaxies to form, while a slower one would have collapsed everything back into a cosmic crunch before life could emerge. This observation lies at the heart of the anthropic principle, an idea that straddles the line between science and philosophy. In its simplest form, it suggests that the universe must be compatible with life because, well, we're here to observe it. But interpretations diverge sharply. The weak anthropic principle treats it as a selection effect. We shouldn't be surprised to find ourselves in a life-permitting universe, because only such a universe could produce observers. The strong version goes further, proposing that the universe's laws somehow require conscious life to emerge, hinting at a deeper teleology woven into reality itself. Critics dismiss fine-tuning as a cosmic coincidence or argue that we simply don't yet understand the underlying physics that might explain these apparent miracles. String theory, for instance, posits a landscape of possible universes with different constants, a multiverse where countless dead-end realities exist alongside our improbably hospitable one. In this view, we're not special. We're just the lucky winners of a cosmic lottery with near-infinite tickets. Others propose more radical solutions, like the simulation hypothesis, where our universe's precise parameters reflect deliberate engineering by advanced intelligences. Yet the debate isn't purely academic. It forces us to confront profound questions about existence. Is the universe inherently biophilic, or are we the fleeting result of a statistical fluke? The answer, or lack thereof, reshapes how we see our place in the cosmos. For now, the anthropic principle remains a tantalizing puzzle, one that challenges us to distinguish between the limits of our knowledge and the true frontiers of reality. Whether it reveals a deeper truth or merely reflects the boundaries of human understanding, it reminds us that the universe's greatest mystery might be the fact that we're here to ponder it at all. The next chapter of human space exploration isn't just about planting flags, it's about building homes. Mars, once the stuff of science fiction, is now the focal point of an unprecedented push to establish humanity's first permanent outpost beyond Earth. SpaceX's Starship, designed to carry 100 passengers per flight, could make the red planet reachable within this decade, while NASA Artemis program lays the groundwork for lunar bases as stepping stones to deeper space. But colonizing Mars isn't just a technical challenge, it's a test of survival. Imagine domed habitats pressurized against the thin atmosphere, powered by nuclear reactors or solar arrays, with underground tunnels shielding settlers from radiation. Every breath of air, every drop of water would need to be recycled or extracted from the rusty soil. a closed-loop system where failure isn't an option. Yet Mars is just the beginning. The asteroid belt holds riches beyond Earth's wildest dreams, metals like platinum, gold, and rare earth elements in quantities that could transform our economy. Companies like Planetary Resources and Astroforge are already developing spacecraft to prospect and mine these celestial bodies. A single platinum-rich asteroid could contain more of the metal than has ever been mined on Earth, fueling everything from electronics to clean energy technologies. The challenge: developing robotic miners capable of operating in zero gravity, where a single misstep could send valuable ore drifting into the void. Private companies are rewriting the rules of space access. Blue Origin's New Shepard and Virgin Galactic's Spaceship Two have made suborbital joyrides a reality for paying customers, while SpaceX's reusable rockets have slashed launch costs by 90%. This isn't just about tourism, it's about creating an infrastructure where space becomes an extension of human industry. Orbital hotels, like those proposed by Axiom Space, could host researchers or wealthy adventurers, while startups experiment with manufacturing drugs and alloys in microgravity, where crystals grow purer and materials blend in ways impossible on Earth. International collaboration adds another layer to this cosmic expansion. The Lunar Gateway, a joint project between NASA, ESA, and other space agencies, will serve as a staging post for missions to Mars and beyond. China's ambitious plans include a moon base shared with Russia, while India's space program aims to land astronauts on the lunar surface by 2040. Even smaller nations are joining the fray, with the UAE's Hope probe studying Mars and Luxembourg pioneering asteroid mining laws. This isn't a race, it's a collective leap where shared knowledge and resources could make the difference between success and failure. The ultimate goal, not just survival but thriving. Terraforming Mars, though centuries away, is no longer pure fantasy. Scientists speculate about releasing greenhouse gases to thicken the atmosphere or deploying algae to produce oxygen. Space-based solar power stations could beam clean energy to Earth, solving climate crises while powering orbital megastructures. And as propulsion technologies advance, from nuclear thermal rockets to theoretical warp drives, the solar system could become humanity's backyard, with generations born and raised among the stars. This future isn't guaranteed. Radiation, isolation, and the psychological toll of deep space travel pose monumental hurdles. But the blueprint is there, written in the ingenuity of engineers, the courage of astronauts, and the collective imagination of a species unwilling to be bound by gravity. Every rocket launch, every rover landing, every experiment in orbit brings us closer to a reality where Earth is just the first chapter in humanity's story, and the cosmos our infinite frontier. Look up at the night sky, and you're not just seeing stars, you're seeing a mirror reflecting your own cosmic ancestry. Every atom in your body was forged in the heart of a dying star, scattered across the galaxy by supernovae, and assembled over billions of years into the miracle of consciousness. That iron in your blood, it came from a stellar explosion older than our solar system. The calcium in your bones, a gift from colliding neutron stars. You are, quite literally, the universe experiencing itself, a fleeting arrangement of ancient stardust that can ponder its own existence. This cosmic perspective reshapes how we see ourselves. Earth, when viewed from Saturn's rings by the Cassini spacecraft, appears as a pale blue dot, a single pixel suspended in a sunbeam. All of human history, every war and invention, every love story and whispered secret unfolded on that speck. It's a humbling realization, but also strangely unifying. The borders we fight over vanish at cosmic scales. The divisions we cling to melt away when seen against the backdrop of 100 billion galaxies. Yet this vastness isn't oppressive, it's liberating. The universe doesn't care about our mistakes or triumphs, but that very indifference means we're free to define our own meaning. We are the universe's way of understanding itself, and that comes with responsibility. The same cosmic forces that shaped us now allow us to shape our future, to protect our fragile planet, to reach for the stars, and to ensure that the story of life doesn't end with us. Consider the Voyager golden record, hurtling through interstellar space with sounds and images of Earth. It's more than a time capsule, it's a testament to our cosmic curiosity, our refusal to be bound by the limits of our cradle. That urge to explore, to connect, to scream into the void, "We are here," is perhaps our most human trait, and in a universe where matter can become conscious, where stardust can dream of distant galaxies, that might be the most astonishing thing of all. This perspective doesn't diminish human life, it elevates it. We are transient, yes, but also extraordinary. The universe's way of turning hydrogen into wonder, gravity into poetry, and light into understanding. The cosmos wrote the rules, but we get to play the game, to ask questions, to seek answers, and to keep adding new verses to this grand cosmic story that began with a bang and through us found its voice. From the first searing moments of the Big Bang to the silent expanse of dark energy stretching space itself, we've traced a story written across 14 billion years, a story where hydrogen becomes galaxies, stardust becomes consciousness, and the void becomes a canvas for unimaginable wonders. But here's the breathtaking truth: this isn't just history. The cosmic story is still being written, with every telescope pointed at the stars, every probe landing on distant worlds, and every experiment probing the fabric of reality. We're not just observers of this grand narrative, we're active participants, adding new chapters with each discovery. Think about how far we've come. A century ago, we debated whether the Milky Way was the entire universe. Today, we know it's just one of 2 trillion galaxies, each with its own stories of birth, collision, and evolution. We've decoded the nuclear furnaces of stars, unraveled the gravitational dances of black holes, and even glimpsed the afterglow of creation itself in the cosmic microwave background. Yet with every answer comes a deeper mystery: dark matter's invisible grip, dark energy's relentless push, the quantum strangeness of the subatomic world. These aren't just puzzles. They're invitations to keep exploring, to stay curious, to embrace the humility of not knowing while daring to imagine what's next. This journey isn't just about science, it's about perspective. When you realize the atoms in your hands were forged in ancient supernovae, or that the light hitting your eyes left distant stars before human civilization began, the universe stops being out there and becomes part of you. That shift changes everything. It turns the cosmos from a spectacle into a home, a vast, wondrous home we're only beginning to understand, and the most exciting part. The next groundbreaking revelation might come from a backyard astronomer, a student analyzing telescope data, or even a comment in this very discussion. The universe doesn't discriminate, it reveals its secrets to anyone willing to look, question, and wonder. So keep gazing upward, keep asking why and how. Because the greatest stories aren't just told, they're lived, and ours, against all cosmic odds, is just getting started. What do you think the next big cosmic discovery will be? Drop your thoughts below, and let's keep the conversation as infinite as the universe itself. Don't forget to subscribe, we've got so much more to explore together. Until next time, keep looking up, the cosmos is waiting.